I'm going to speak about, so large part of the talk is going to be about testing the quantum nature of gravity, okay? So you have heard already in this conference a lot in this direction, but I'll be going about justifying a little bit the things which go behind the scheme that we proposed. And then towards the end, we will have a new scheme for, a new tool for seeing the quantum nature of large masses. Okay, and also earlier, some briefly allude to some methods for preparing, superpositions, large masses. Okay. So the outline of the talk is first I'm going to spend some time motivating what the main motivation, which is to find the, I would say, hitherto hidden quantum origin of the Newtonian interaction. Okay, so of course people can doubt whether it's quantum or classical, and so far in all experiments to date it is hidden whether it's quantum or classical, and this can be unraveled with the type of experiment I'll discuss. And just to clarify at the outset, what I mean here by the Newtonian interaction is the causal, the retarded Newtonian interaction as would arise in a relativistic theory of gravity. It is only of that kind of Newtonian interaction that we can prove the quantumness of gravity, okay, with that kind of interaction, Newtonian interaction. If it was as a la Newton, action at a distance. Yeah, so I read somewhere Newton was quite disturbed by this action at a distance, but he had no alternative. Then that for that we cannot prove anything. Okay, but it is the causal Newtonian interaction for which we can prove. Okay, now of course when I want to say something is quantum, we must actually go the other way around. We must also, define what at the outset what we mean by classical, okay, and then say that under those definitions you will not be able to do something which is, namely here is the production of entanglement, and then we can say, we can show that how entanglement is produced in the scheme we use. And then we will have a schematic proposal. Okay, this has been alluded to a few times in the conference, but I will present this again in a clear manner. Okay, and then a little bit of history if I have some time. Okay, then I will briefly allude to some of the experimental challenges. So this is a foundations conference, but there will be a couple of slides regarding the experimental challenges, in which of course there are better experts, actual experimentalists in the audience, but anyway, we have made some estimates here to help them on that way. Okay, and then in the end, I'll introduce a new tool for exploring the non-classicality of macroscopic masses, which are free. Okay, not tethered or not clamped, just free macroscopic masses, free falling after release from a trap. Okay, right. So let me start with the gravity side of things. Okay, so an important open question is whether. Okay, so it's not what type of theory is the quantum gravity theory, but whether gravity is quantum. Okay, and one may initially think as it is most in the traditional community. Okay, so I'm speaking to the foundations community here, so they are fully with me. Okay, but people would naively first try to think about using old quantum mechanics, okay, so which is things like energy level quantization or order of h-bar corrections to potentials. So at the outset, I stress that these are extremely, extremely hard if gravity is concerned, okay. For example, if you have the standard gravitational waves people are detecting, if you want to detect a single graviton from that, it will cause a nanokelvin, fluctuation in temperature on the whole apparatus which is detecting it. Okay, so that's how hard it is. Okay, I'm not telling the experiment I'll be suggesting is any easier. Okay, well, hopefully much easier than that, but still very hard. Okay. and corrections to Newtonian potential, okay, due to quantum, okay. So as people have found corrections due to the quantum nature of the field in the case of electromagnetism, there have been much more prominent corrections, such as the lamp shift, etc. Here, those corrections are extremely small, okay, at reasonable distances. So there's not much hope, okay, to use those avenues. I tell this more to when I speak to say a particle physics community. Okay, that is the more important thing to stress. But here, definitely, a lot of you are with me when we say that let us use something else. Okay, so let us use concepts which are coming post the quantum information revolution. Namely, let us use the entanglement conveying ability. Okay, which is a non-classical property. Okay, and I am being a bit sloppy here. That when I say we are testing quantum, what we are truly doing, I acknowledge fully beforehand that we are testing just a non-classicality, one non-classicality according to the classicality definition that I will give. Okay, but does not mean, I mean, quantum mechanics is a huge baggage coming all together. Okay, so of course the superposition principle is sitting at the core, but there is the unitary evolution and the quantum measurements, right? So all these three things are coming together. Okay. And we are testing one aspect, one non-classicality, okay? Whether we are testing wholly quantum mechanics is not possible to say immediately, okay? Also, I heard a few of the earlier talks in the conference, so I will allude to a few of the other speakers' comments and questions in their talk as I proceed, okay? And for that aspect, I'm just putting up an important slide here. Okay, this is kind of a backdrop. Okay, is how gates are usually done in quantum information in between qubits. Okay, or at least this is emerging as the preeminent, most important way of doing gates. So it is extensively used in ion trap quantum computing as well as very largely in superconducting quantum computing. Essentially, we do connect to qubits by a bus, okay? But this bus, a quantum system, is always just virtually populated or virtually excited, okay? The bus does at no point does go to a different state, okay? It remains with a huge overlap in its initial state. Still, a coherent interaction happens between qubit 1 and qubit 2, okay? And what nature does, essentially, this is just a directed interaction between two qubits, but what nature does when you have interaction between two entities is exactly this, but just in empty space. Okay? So let me clarify a little bit more from some very historically important examples. Okay, so Harosh implemented this experiment, but by two atoms going through an empty cavity. And so the cavity was unpopulated in the vacuum state, but the qubits became entangled. Okay. And the scheme was proposed by Zheng and Guo shortly before Harosh. Okay, and what you can see, this is simply second-order perturbation theory. I usually find it very instructive that you go to the second-order term in the Dyson series for the unitary evolution. Okay, it is h t dashed double integration. So if you do that, then if you start with the Hamiltonian, where each qubit is coupled to intermediary system. This is the A and A daggers, a harmonic oscillator. Okay. Then if you detune highly so that there's no energy match, okay, then what happens is to the second order, you get this kind of term. Okay. This is the term I've copied and pasted from their paper. So you see the second term in the lower line is this flip-flop interaction between the qubits. Okay. But you see, there is no mediator left in this term, okay? So it's really a coherent interaction. So if this interaction happens just by observing the two qubits, you would never be able to say that there was a mediator, okay? Just like gravity, okay? However, we should not forget that what they are hiding here in this expression is this AA dagger equal to, so there's a AA dagger factor, a commutator, okay, which we know is identity. That's why it's not occurring, okay? However, you see, if this was a classical system, okay, this commutator would be 0. Okay, so there's no point of, since the second order term comes with this AA dagger commutator, okay, this term would be 0 if you had a classical system. Okay, so this is one of the quickest way to convince that you still need a quantum mediator to do this interaction between the qubits. The qubits have a coherent interaction. However, if this bus was classical, you would never have. Yet the interaction is such that only the qubit operators are involved. There's no bus in that interaction description. Okay, yet if the bus was classical, you will not have that interaction. This will just go to 0. Okay, I tell this point because this thing appeared in, I think, on the very first day in Thomas's talk, that maybe one can find a bus, okay, from some, say, fleeting impurity or of the mixedness of the interaction. But the point is that if it is in this, if an interaction happens in this kind of way, virtual particle mediated, you never have any evidence of the mediator from the coherent evolution of the qubits alone. So the mediator must come in as an extra assumption, okay, justified by some other means. Okay, so again, a historically famous paper, the Sorensen-Molmer gate. This is another way of writing the mathematics. Again, you see that here atoms, these E and G, correspond to atoms. Okay, so the atoms always remain in their, same kind of, so they are going between this GG and EE state. Okay, but in these intermediate states, many higher levels of phonons are, all the higher levels of phonons are involved. Okay, and this effective interaction is where you see the quantum thing is that you have to go in for a coherent superposition of all the intermediate phonon states, okay, to have this effective interaction. At the same time, in the beginning or end of interaction, the phonon states are exactly the same, and so you do not have any evidence in the mediator. Okay, in this effective interaction. Okay, so a more standard way of showing this is this second order term in perturbation theory. Okay, and the first order term is what causes can cause entanglement between a system and a mediator. Okay, but if you are looking at only the two systems alone, okay, their joint state, then it's only the second term which is acting. Okay, so this is the first order term is bit like decoherence due to gravitational waves. Okay, the second order term would be the Newtonian interaction. Okay, now let's say the so here so if you so this is very can be this previous expression which I have written schematically here can be done in a fully relativistic covariant manner, as is known for a long time. Okay, using propagators for virtual gravitons. Okay, so instead of photons or phonons, which are virtual in quantum information applications, very perfectly coherent two-qubit interactions, it is the same thing for gravity, but it's of course virtual gravitons in this picture, and you get the Newtonian interaction. Yet the problem is all experiments to date that people have done, okay, cannot distinguish between whether it is a quantum mediator or a classical mediator. Okay, with the existing experiments, it is it has not been able to separate out these alternatives. Okay? The classical here, of course, I have schematically presented like this observed system, so observation should not make a difference. Okay, so we are trying to find out here whether gravity really works at least in this weak perturbative limit in which we are working. Okay, so Newtonian interactions of a small mass is what we will take, where you can regard gravity like a field in a Minkowski background. Okay, in that kind of regime, is gravity exactly like the other forces? Okay, through photons or gluons which are exchanged for the other forces. Or is it qualitatively something different? Okay, this is the question we are asking. Okay, now what we are going to use is that when it's a quantum exchange, then you can entangle masses, and when it's a classical exchange, that you cannot entangle masses. Okay, I'll justify a bit more, but of course, as was important from Thomas's talk on the first day, it is true that we have to be careful that the initial masses are highly pure. Okay, they are completely unentangled and completely pure states. Okay, to a very good approximation. Okay. So then, under those circumstances, a classical mediator, a continuously observed mediator, cannot entangle them. Okay. Now, what are the assumptions which are going behind, okay, such a thing? Okay, so we have spelled this out very carefully in this paper by Ryan Marshman. Okay, so as I said, the mediator cannot be justified from within the mechanism, okay, because it's completely eliminated. It's a virtual interaction, okay, but yet it is very important for it to be there. If it made classical, then this interaction will just go to zero, exactly zero. Okay, so we have to justify the mediator from something else. Okay, and this is why I said at the outset that we are proving the quantum nature of that kind of gravity, which is relativistic gravity. Okay, so we have to appeal to this known knowledge that we have relativistic causality, and relativistic causality justifies that you have to have a local interaction. Okay, so if you have a local interaction, then of course you can have only local operations. Okay, so relativistic causality necessitates that we have only local operations on our system. So if you have a mass here, it interacts only with the local gravitational field, and if another mass here, it only interacts with the local gravitational field. So local operations is very well justified in physics. Okay, definitely over the time scale of the separation scales which we are talking about. Okay, there could be non-locality in nature on very small times, separations, but in the locality of interactions is very well justified. Yeah. And of course, this is not quantum non-locality I'm talking about. It's not the Bell non-locality, but this is just the locality of physical interactions. Okay? It is a mystery, of course, why interactions in nature are local, but they happen to be. Okay, and this underpins relativity. Okay, now. Then, of course, the other thing is, rather than an assumption, it's kind of a definition of what we think is a reasonable definition of classical. Okay, so what is our reasonable definition of classical? It is that, so I have denoted in this slide the gravitational field in terms of this h mu nu, which is what people use to depict weak gravity on a flat space-time. Okay, so it's like, now you can think of it like a field at every point in space-time. Okay. If you can think of it in that way, or you can think of it in terms of curvature, but the main point is that it is a number at every point. Well, it's a tensor at every point in space-time. Okay, so many numbers. Okay. And what does mean it to be a number? Means that you can accurately measure it. You can depict it with strings of bits, many bits, arbitrary large number of bits. Okay, and you can perfectly measure and ascertain it. So I think this definition coincides with the definition given in John's talk a couple of days ago. But yeah, probably coincides. Yeah, but this is a very reasonable definition. This is how we learn about the definition of fields ourselves. Okay, in university, that classical field has a value at every point in space-time. Okay, what I am allowing here is for the matter, these J, Ket, and Bra are denoting states of matter, the sources of gravity. That can be any quantum state. Okay, J doesn't have to be a specific basis, can be any quantum state. And all those quantum states can happen with different probabilities, Pj, so there can be perfect mixedness in the setting. And they source different kind of classical gravitational fields. Okay, this is what I'm demanding. Okay, so if it's a classical gravitational field, of course, it can do only classical communication. Okay, I cannot do quantum communication with you through this Zoom I'm speaking. One has to use a satellite and photons to do that. Okay, so this is purely classical communication, which is possible through the field here. Okay, and what I'm allowing extra from usual definitions are I'm allowing fluctuations. Okay, again, this slide is not so much targeted at the quantum foundations information audience, for whom it might be quite obvious, but often this is put because people often think fluctuations are quantum. Okay, but of course you all know that fluctuations are alone not quantum. Okay, so fluctuations into non-complementary basis are needed at least to show quantum. So this is why if you have randomly fluctuating gravitational fields, I would say that is a classical statistical ensemble. So that I'm fully allowing. Okay, those fluctuations I'm still allowing, but they do classical communications. Okay, then comes this slide that, of course, under the setting that I have described, what has happened. So we can apply local operations. Local operations can be anything of those things described here. It can be a very large set. Okay, and the classical field always representable by string of bits. So classical field can only do classical communications. Under this setting, if you started with pure unentangled states, it's very easy to show that, this is simplest string with unitaries. But if you started with separable states of this form, okay, not a priori correlated with the environment, okay, then you can also show that it will go to separable states. Okay, so this is the LOCC proof of standard quantum information. So there's no chance that you can entangle under those two assumptions of the last page. Okay, the field being classical and relativity. Okay, so relativity is an assumption. So locality is an assumption. Physical interactions. Okay, now. To the schematics of the setup. Okay, so hopefully I have justified, and of course you can ask me later on that by using classical field, and if you have locality of physical interactions, you cannot entangle. Okay. Now let's take two gravitationally interacting masses, and we place each of them in a superposition. Okay, we have these separations delta x. Okay, now what happens? Okay, so it's a simple side. We start with L plus R for both of these things, and then there's a phase evolution. Okay, the phases are just according to E equal to h nu. Okay, so g m square by r. Okay, divided by h bar is the frequency into the time. These are the phases accumulated because the distance separations are different from the different components. Okay. Now, we can rewrite this. We can take out the common part of the phase because RR and LL are the same phase. And as you will see, the complementary part, okay, the L plus e to the power I delta phi LR and R and this I delta phi LR, L plus R, these are not the same. Okay, so generically, this is not a factorizable state. So after some time evolution, okay, these two masses end up being in an entangled state. Okay, as soon as these are not the same. Okay, which is an arbitrary small time. But actually, if you can wait long enough for these two to be equal to pi, then this is even a maximally entangled state, like a Bell state. Okay? So now we want to estimate a magnitude of the effect. Okay? But we are going to make a very optimistic estimate of the magnitude of the effect. So how can we do that? Okay, so to do this optimistic effect, we have to, at the outset, take this kind of regime where the closest separation between two masses, okay, so the right for the left mass and the left for the right mass, is the only distance under consideration. The separation size delta x's are so large, okay, that you do not have to consider the other components. Okay, the separation is much larger than the closest approach, d minus delta x. Okay, so that is the crucial criteria here. Okay, so if you take that criteria, then you can see that you can neglect all but one of the phases. Okay, this is only one of the phases which will dominate. Okay, and this is a very important regime to see the best possible amount of the effect. Okay, but before we get too carried away, we have to know what is our limitation on this closest approach. Okay, unfortunately, the limitation of this closest approach is dictated by pretty fundamental things of nature. So we cannot bring them too close. Okay, we can easily make masses neutral. okay, these experimentalists can do now. Okay, perhaps we are lucky enough to have so good single crystals that there are no multipoles inside. So all those can be done. A lot of electromagnetic fields can be circumvented. What cannot be circumvented at all is this Casimir interaction. Okay, so it will happen still between neutral dielectric objects. Okay, and its dependence is pretty much on fundamental constants. Okay, so if you want gravity to dominate, you see, you end up with things where you do not have too much control about. This mp square is Planck mass square, and this is, so distance is literally the only free parameter. Okay, densities of objects. Okay, so Marcus made an important point in his talk. Okay, so you have to use densities of solids. Okay, to do this experiment at all. Okay, for that gravity dominates with that density. Okay, however, density of solids has a limit. Okay, people can use something like osmium whatsoever, but there's a limit. So if you take standard solids like silicon, diamond, okay, then you will see that irrespective of the mass, you do not get anything by making larger masses larger. Okay, if you do not do any screening can improve things of the electromagnetic interaction, then the closest distance you can come is 200 microns. Okay, so this is a big problem because the splitting size has to be, in this limit I'm considering, is much larger, but at least comparable or a little bit smaller in realistic situations with respect to the separation. Okay, so this pushes us to this hundreds of micron level superposition if you are not screening the electromagnetic forces. Okay. And then this is related to a point which came up again in this. So this slide has a lot of information. So I'll go in 2 steps. So it has 2 types of information. Okay, so let me do the first type of thing, which arose I think in a few talks, Thomas's talk and Marcus's talk, and then there was a question by Kaslav on that matter. So I want to clarify something here, is that you can indeed consider this limit when the superposition size is so large that I'm not telling this is an experimentally good limit, okay? It's experimentally maybe ridiculous limit, okay? But in principle possible that the masses are much closer than the superposition sizes, okay? In that kind of limit is the full 1 by r, which is used to grow the phase and entangle, okay? It's only when you consider a case, which is the much more realistic case, that the superposition size is much smaller than the center of separations of the interferometers, that you have to expand this 1 by r order by order. Okay, when you order by order expand, then it is true that the first order effect, okay, is just the acceleration. That's the force of the masses towards each other, and that acceleration of the center, of course, does not entangle. It's the relative acceleration which entangles. Okay, so it's the curvatures of the one mass which the curvature is responsible for the entanglement. So it is, if you expand by delta x by the separation, it is indeed a second order or higher effect. Okay, but if you just try to use the 1 by r, you can get a much stronger effect. Okay, that's the thing. So you do not need to expand 1 by r order by order. You just try to use the full 1 by r. Then we can see that if we put microspheres, okay, and then time of 1 second is enough. Okay, even with this 200 micron separation. Okay, of course, if you are to use screening and can reduce this, then it is even better. Okay, but of course, screening, we'll talk a little bit about it if possible, but it brings other complexities, okay, to the question. Okay, now why is this effect becoming so dominant? Okay, so in our paper, we just wrote that Planck's constant, also being a small thing, is able to fight the gravitational constant. Okay, so 2 small things fighting against each other, which is partly correct. Okay, but another thing which is playing very important is that the masses are becoming larger, and is the way in which Marios and Carlo put it in one of their papers, is that the mass is kind of it's still much smaller, 10 to the power minus 14, 6 orders of magnitude smaller than the Planck mass, but kind of getting there. Okay, and you can rewrite the interaction in this way, and then there's this c into tau makes up more than for it. Okay, that this decreasing order. Okay, so it's the gravity becoming larger with mass plus the Planck's constant being very small, which together helps these phases to be dominant enough to have a Hertz effect, 1 second effect, even when the masses are 200 microns separated. But this is only at this ridiculous, well, at this very, thought level that you can create superpositions which are much larger than 200 microns. Okay. Of course, we did not do our calculations based on that in the paper. You can read, we took much more modest settings and we got some value. Okay. And so just a little bit of history that, of course, Feynman already spoke about a very similar setup, and he told that, to describe this experiment means, in some sense, all aspects of this kind of experiment, one would need, quantum gravity. Okay. However, so he did not really emphasize what aspect. Okay. It turns out to be that entanglement is the thing you need to explore. Okay. Because it's a multi-particle interference, essentially, two-particle, effect. You cannot do with anything lesser than entanglement. Okay. And also the what he was trying to use is the acceleration in his words. The accelerations are very small. Okay, they are not amplified by this Planck's constant factor. So we would rather use the phase evolution here. Okay. Now, a little bit of something which other people have proposed from time to time is you create a non-classical source of gravitational field by superposing a mass, and then allow a second mass to pass, okay? And then, of course, the second mass can go randomly to left or right. You can measure that, okay? But what I emphasize is that kind of test will only test the classical stochastic nature of gravitational field to be, with probability P in the left, probability R in the right, PR in the right, okay? So it will not test the quantum coherence between the L and R centered gravitational field. So if you have to test that, I don't think there's anything simpler than testing for the entanglement, okay? Or if there's any other thing which will be of similar complexity, okay? You have to at least do this order of time experiment, the schemes which are as good as entangling them. Okay. Now, of course, I come to the requirements. Okay, so we need this large mass, large splitting and long duration superposition. Okay, so how do you go about creating them? Okay, many things have been suggested in the past. I just say that the standard naive way of using a beam splitter, okay, does not work here for this kind of masses, simply because of this kind of exponential falling of the transmittivity. A beam splitter is nothing but a barrier, potential barrier. So you just cannot say you have a huge mass and you have a perfect beam splitter for left and right. Okay, so so ideal Mach-Zehnder does not work. Okay. So what can one do? Okay, so one technique one can use is to prepare a spin in a up and down state. Okay, and then use the Stern-Gerlach effect and accelerate it oppositely. Okay, so we have discussed this in a number of papers, you can see, and I will not go into the detail. More recently, we have encountered some technical issues, limitations also of the naive application of this protocol, okay, so which we are trying to think about, but so some limitation in the superposition size. But for the moment, let us forget about this limitation, which is diamagnetism. So just if you forget diamagnetism in the world, then this protocol works extremely well, okay? So if you have a superposition of up and down, a single spin is embedded in each micro object, okay? You have up and down, then Stern-Gerlach creates this splitting, okay? Then at time, quarter of the time of the experiment, you flip the spin, okay? It decelerates, stops, then accelerates oppositely, okay? Then at 3/4 the period, you again flip it, okay? So that it comes and overlaps both in position and momentum, okay? You need that because we are only going to measure the spin, okay, to find any say relative phase or something like that. In our case, entanglement. Okay, so you need to bring the motional states exactly to coincidence. Okay, this type of experiment has been done with atoms by Ron Follman for a long time. Recently, we also published with him, but his experiments are in his group. So this can be done with atoms, but one wants to do with nano objects. Okay. So how will the experiment take place? You will have traps in which you would have, cooled micro objects and dropped them, then subjected to the Stern-Gerlach fields, okay? And you have to add a little bit of an extra element that at one point you have to map the electronic spins to nuclear spins so that the masses fall directly, beside each other and have this nice time to gain the phase. Okay. And then if you substitute all that previous maths, okay, with with the left and right just replaced by left up and right replaced by right down, okay, you will see that you will end up the spins becoming entangled, okay, which you can measure with this weakness. Okay, so this is the thing. You do the whole experiment. At the end of that, you just measure spin correlations, okay, and those spin correlations are going to give you a weakness. Okay, so I'll speed up a little bit, okay, because we are coming more to experimental issues
so
now.
You have 5 minutes.
5 minutes left, yeah. So
and
I
then
think
10 minutes for questions.
Okay. Yeah, so I will speed up a bit. So what we can put a screen that helps a bit, that helps to reduce the magnetic field gradients required, the masses required by one order, and also splittings and hence separations, required by one order. Okay, why doesn't this screen help you to go to just smaller, like micron? Okay, it's because the trajectories also get perturbed. Okay, so we don't know a good way to bring the thing together. Okay, when you have this screen also, so it helps by one order of magnitude in everything. Okay. There are many noises. Okay, so we have analyzed these noises in recent papers. Okay, there's so essentially you need 10 to the power minus 16 pascals of pressure, 150 millikelvins of temperature to have the coherence for the second. Okay, what is a new kind of noise? Okay, is this noise from external masses. Okay, they give random accelerations. Okay, and what can you do for that is a very simple idea. This is a paper by Marco Toros and others, is that you really have to put the whole experiment in a freely falling lift. Okay, then all these external accelerations due to random masses get cancelled. Okay, and only the entangling effect, which is due to the curvature of the two masses, remain. Okay, of course, the curvature of these faraway masses have a deleterious effect, but that can be counteracted. Okay, so I think I seem to have lost those slides here on the details of this paper, but we made estimates. Okay, I will quickly go to this other kind of scheme before finishing. This is our new work. Okay, recently done. Okay, so we want to use masses which are described by continuous variable systems usually. Okay, like qubits. Okay, what is the advantage of using masses, being able to use masses as qubits even when they are spinless? Okay, when they are spin full, we are kind of using the spin as the qubit and doing things to masses with that, but the advantage will be that a host of quantum protocols are in terms of qubits. Okay, and what we transport here is an idea which has been used for photons a lot. Okay, which are called photonic qubits. Okay, which are the spatial states of photons. Okay, as qubit states. So suppose you are able to prepare a mass in a superposition of distinct locations. Okay, I have told how to prepare it with a spin. Then later on, you can measure and disentangle the spin, or you can use some methods which we proposed from Vienna some time ago, where you use some projective measurements to prepare. Okay, that can work even for a spinless case. Okay, but once you have prepared, you can measure that continuous mass pretty much in a qubit basis, and this is very obvious when you see it. Okay, so you have masses 0 and 1, these are free masses, you have free evolution, they interfere. Okay, then you place detectors. Okay, if the detectors are measuring in these purple places, then it is a Pauli Y measurement. Okay, so corresponding to -1 and +1, and similarly you have Pauli X measurements. Essentially, wherever you measure the mass, it's a POVM according to that relative phase. Okay, so essentially you can measure the output of an interference instead of a continuous, interference fringe. You can interpret it as a qubit measurement. Okay, so that's the power of this tool, and we have found that deploying it for much more macroscopic masses than have non-classicality been demonstrated to date is possible. Okay, so you go to 10 to the power -19 kg masses. Okay, and then you need angstrom resolution detectors, and then what you can verify is the the entanglement, the spin path entanglement in a Stern-Gerlach state. Okay, this has never been tested till now, unfortunately. Okay, even for an atom. Okay, but you can do it in this kind of way, and that is also happens to be a test for a state-dependent state of quantum, contextuality. Okay, so all you do is you measure the spatial qubit, as I said before, and you measure the spin qubit also. Okay, in a detection finally, and then you can do a Bell correlation, and you can verify this non-classicality. Okay. Similarly, you can also entangle two distinct spatial qubits in this kind of way, okay, in a very non-Gaussian state, as you see. And our technique enables, it's a qubit technique, so it enables you to verify this non-Gaussian entanglement. Okay, creating and verifying non-Gaussian is still very much open in the field of nano objects. So you can do with, again, with 10 to the power minus 19 kg masses, okay, and you can use the Casimir interaction to entangle. Okay, what does this test? It tests not only non-Gaussian entanglement, but also a fundamental thing. I mean, I would like to stress it a little bit, is that whether forces, you could equally take the view that macroscopic masses remain quantum themselves always, but the forces between macroscopic objects become classical. Then we would not know any way to, distinguish. So we would still see the world very much, we would still see something like a collapse, okay, because we, even if just the forces became classical. So those kind of things can be tested also fundamentally here. Okay, the catch is that we want to measure the entanglement on the same state. So the interaction is evolving the state. So the Pauli Z measurements, which are just finding whether it's left or right, and the Pauli XY measurements, which are after the wave packets overlap, have to be nearly at the same time. Okay, if the system evolves too much at the intermediate time, then we are gone. It's on the same state that you have to do these measurements. So that brings this unpleasant thing here, that you have to, after this time, you have to squeeze the states irrespective of knowing whether it's 0 or 1. So you have to have the same oscillator varying time potential acting on both of them, so that coherently you squeeze them, so that they spread so rapidly that you have these measurements around the same time. Okay. Yeah, I will skip this because we can come to this in questions. Okay, so these are the papers I referred to, alluded to, and yeah, I can take some questions.
Thanks, Sougato, for the nice talk. So I will start maybe with some question from the audience here in Vienna. Is there any question? Do you have some? Yes. Nobody? Yes. I don't know. I can keep up some. Yes. Sorry.
Hi, Sougato, it's Carlo.
Hi, Carlo. Hi.
This is vague. You mentioned the way we had to rewrite the phase in terms of the Planck mass. And I kept going around trying to how to think about that. Mm-hmm. And because the role of the Planck mass in quantum gravity is just totally unclear, even in the best formulated quantum gravity theories. Mm-hmm. So I wanted to ask you whether it could be seen in the following way, but this might be completely off. But this experiment is a sort of interference experiment, after all.
Yeah. Mm-hmm.
And so if I think about optics, and the kind of phenomena that distinguish the sort of the Eichhorn limit, the rate propagation of light from the ondulatory optical phenomena. An obvious thing is that if you have a hole in a wall, light behaves in a certain manner if the wavelength is much smaller. And then when the wavelength gets right to that, to the order of magnitude of the hole, you start seeing things like interference, diffraction stuff. is there a sort of an analogy here? Is that possible that the Planck mass comes out in a way vaguely analog to the size of the hole, through which one should get to that mass, to that order? It's not a very good analogy, but is there something like that, or?
No, that is a very interesting question. I mean, definitely these are kind of, it's a threshold near which you need to go. And then when you are far beyond that threshold, again, things are bad very, very fast. Yeah, I mean, one can think of something like that. I mean, don't know. Okay, and in a very different context, we found something interesting recently. So I didn't allude to this paper. So if you just take just the presence of a mass, suppose a mass is assembling from from smaller parts. Okay. So the vacuum gravitational field modes, okay, so these are on-shell modes, would actually become excited as this assembles, okay, and from that excitation would go to like e to the power minus m by mp square whole square. So they would become too classical or very large numbered, okay, like I would say that everything is always still quantum. So very classical here, I mean that very difficult to infer its quantumness, okay, in a very large thermal state, for example, will become at the rate of the ratio of mass to Planck mass, okay, exponentially e to the power minus m by mp square. But in context of this interference experiment, it comes in a I mean, the same factor comes, not in an exponential way, but if you see from the phases, if you randomize phases slightly, then it can again go to the similar factor, you see. So we haven't thought much about that. It's a good question. One can.
Thank you. Yeah. Thanks.
Are there further questions from the audience? No. Maybe I have a question on the initial part of your talk. So you mentioned this role of the mediator, even with the example of the electromagnetic field. So if I understood correctly, so you always have to assume a mediator, otherwise you will never see. So you cannot see the effect directly on the affected particle. So maybe could you comment a bit more on that?
Yeah, so I think the best slide for that would be this one. Yeah, so this is just how people make qubits interact in say between superconducting qubits through a microwave waveguide. Okay, so the superconducting qubits have an interaction due to the microwave waveguide. Okay, but in that interaction, you see, the microwave waveguide is never present in the explicit form through the second order effective interaction. Okay, the photons come only as this a dagger commutator. Okay, so essentially as like an identity. Okay, so it is important, yet so it is important because, of course, if you took you can see this from here. I mean, a and a dagger commutation will be zero classically. Okay, doesn't make sense classically. So the interaction is uniquely coming due to the quantum nature of this mediator, right? Yet, the state of the mediator, okay, is not influenced at all. So if it is vacuum, it will always remain vacuum. Okay, so this is the nature of virtual interactions, that the mediator does not change. It's always separable and disentangled from the pair of objects. So the objects together has a completely coherent evolution. Okay, and yet the mediator is responsible because it's because of the quantum nature of the mediator that the interaction is at all there. Okay, so this is definitely one way to visualize the thing. Another way to visualize, much more pedestrian, is this. If you write out the identity in the middle in terms of states, all states of the intermediate field. Okay, you will see that initial and final states of the field remain the same. Okay, but at intermediate times, okay, it can go to other things. But this, as a whole, this thing is taken as an effective Hamiltonian, okay, where these intermediate states are not, there's no change of state of the mediator. Okay, perhaps this is even better here. Okay, so to find any change on the mediator, you have to use like the first term in the perturbation series. Okay, but that is like a decoherence of each object. Okay, so then you are really then you have to really extra assume that it's the same mediator which is here is also there, you see, to really conclude anything from this. The coherent interaction part will never have that mediator explicitly involved. Yeah, that's what I'm telling you.
Okay, thanks. Thank you very much. Further questions? Or somebody online? No? You have another question, Carl? Yes, please.
So there was some question, I think, from someone called Nathan. What about ideas of Penrose and Dewey? Yeah. Right. Can they be probed? Yeah. So if I respond to this question in the
okay. So
hi. Hello. Sorry, is there a different question?
Yeah, so maybe you can.
Okay. So guys, Carl again.
Okay.
It's about the last thing you said. Is everything you say is correct, of course, but it's perturbation theory. It seemed to be you describe the terms of perturbation theory as if they were reality in a sense. I mean, what I'm saying is that what actually happened in the in the experiment that in this fantastic experiment that you're describing, it's much more clear if one just doesn't think about the perturbation theory and thinks about the superposition of the two quantum states that correspond to the classical fields, and then one says them changing and coming back and everything. It's just this discussion that you give is it's correct, but I find it's less clarifying than seeing the.
Okay. So maybe so I'll maybe this is a good point for me to go to this last slide, which I did not, So I completely agree with you that the interpretation, for example, in your paper with Marios, okay, about disproving the superposition of curvatures, is a correct way to interpret the result of and the entanglement is the evidence of that superposition of curvatures. That kind of in a cartoon way is there here, okay. This when we have these different centers for exchange.
Right. That's what I meant. Yes.
Yeah, and what I have done somehow is I have spent time describing the quantumness of each of those exchanges, okay, which is the a dagger commutation as well as the n. So that may confuse people that I'm speaking about this quantumness, okay, and my proposal is exploiting a different quantumness, a quantumness of that superposition, right, of these four alternatives. Okay, that's being exploited to get the result. Okay, so my angle is a bit like this, that this quantumness between each of these alternatives, okay, so as I said, it is quantum has no way to be checked, okay, when you take any one of those things. So we are superposing four of those to check these, this local quantumness. But what you're saying is indeed true. So it's not just checking this quantumness, it's checking something beyond that, the superpositions of those quantumnesses as well.
Yes, so we agree. Yeah. Yes, so we went a bit out of time, so there's no time for online question. Let's thank Sougato again.